Hey everybody, so here we are with a quiz on ethers, and I'd like to explain some of the ones here. For this first one, I'm just matching the names. Remember, you have two systems of naming. This here could be called methyl ether or dimethyl ether. That's one system is name the R group, name the other R group, list them in alphabetical order, and then add the word ether to account for the oxygen in between them. The other method is to take your longest chain and call that an alkane. So I have methane or methane, so either one. And then name this as a methoxy group off the methane. So if this is my methane, this is my methoxy group off of it. Okay, so hopefully you guys got the point of that. So I would recommend drawing these out, ethyl methyl ether, and then see what it would be called in the IUPAC naming, where you call the ethyl and methyl. Here, I'll just do one example. Ethyl methyl ether. Here's my longest chain. This is an ethane, and this is a methoxy group off carbon 1 of the parent. So this is methoxy ethane, and you could say one methoxy ethane, but it pretty much has to be one methoxy, right? So we don't almost have to say that. Okay, so that's the first one. For the second one, another reaction map. So always good to practice linking these all together. The point is, this is really supposed to help you with multi-step synthesis thinking. Okay, so multi-step. All right, so here I'm basically adding an OH group here. So it's a Markovnikov addition. So I would probably use oxymercuration here if that's an option. So H2O, and so this is really just a review of alcohol reactions from alkene chapter even. And then here I have a way of making this into an ether. So that would be maybe Williamson ether synthesis. I have either sodium metal or sodium hydride, and then some kind of an ethyl halide, like ethyl bromide or ethyl iodide. And then if I wanted to make this directly here, I could, instead of using this, I could just modify it. Instead of H2O, I could use an alcohol there. So HgOAC2, so this is oxymercuration, but in ethanol instead of water to get this group adding on. And maybe it might help you to think about the mechanism. Remember, the mechanism for that involves a mercurium ion. And then I have ethanol could attack here. Oops, attacks the more substituted side. And that's how I get this, but protonated, and I deprotonate it then. Okay, so I'm not going to finish all of that, but it's basically the same as this up here. All right, moving on, let's look at C. We're changing an ether into alkyl halides. We've got cleavage actually here. So this part turns into one alkyl halide, this part turns into the other, and then I lose this as water. So this is called ether cleavage. So I'm going to usually protonate here and then have my source of bromide attack here or attack here, and this group leaves or this group leaves, and so I get both options here. So my reagent is HBr. Okay. And I'm probably excess, right? Because I need 2 equivalents of Br for that. All right. Once I make that, then I want to do elimination Hofmann style. So I'm going to use a bulky strong base and do heat. So that's E2 elimination. And then I'm going to do probably oxidative cleavage just to get this. And that way I don't have to worry about this carbon and just cleave it off. So that's going to be either ozone or hot KMNO4 also can work. All right, or KMNO4 with heat, and yeah, that would be fine also. And then here, once I have a carbonyl group, then I just need to oxidize it, but I need to also add a methyl group. So I'm going to use methyl Grignard followed by water or acid workup to neutralize it. Okay, now going back up here, then I can go backwards on this alcohol, eliminate to make an alkene. Probably this is tertiary, so I could use H2SO4 and heat and get my E1 elimination going. Then once I have this, I just need to epoxidize it. So I'm going to use MCPBA or some other kind of peroxyacetic acid or peroxy acid of any kind. Any R group is fine. Once I make the epoxide, I want to open it up. When you open an epoxide ring, you always get a tack on the opposite side of that. So I'm picturing either I protonate this and I have water come in and attack here, but this particular diastereomer that I'm looking at is from attack on the opposite side here, right? So probably your best option is NaOH, although it doesn't really matter. Either way, you're going to get a trans 1,2-diol, and you get both enantiomers of that. Once you have that, then we're going to oxidize here, but we're not oxidizing here. Do you know why? That's tertiary. There's no space for that to get oxidized, so we're only oxidizing here. So any oxidizing agent will do, PCC or any of the other ones, okay? And then here we're reducing it back down, but we're also adding a methyl group, so just like over here. So I would definitely use that again. If we wanted to make a syn-diol, do you remember how to do that? Instead of going through an epoxide, I want to use OSO4 or cold KMNO4 and cold dilute KMNO4. Now we'll do this instead of oxidative cleavage. And then once I have a syn-diol, I can turn both of those hydroxyls into ether groups. So I need to have, maybe first step of that is excess or 2 moles of sodium hydride and 2 moles of methyl halide, right? CH3X excess. Okay, so we sometimes we abbreviate it ME or CH3, same thing, methyl group. So it's up to you which one you want to use, but yeah, that's it. And of course, these are chiral, right? So that's why you can also make the enantiomer. It just depends on which side the attack is on. So it's important to realize that you have enantiomers that also form. Ethers are commonly used as solvents. I think you can tell which reasons are not why we like to use them. It's not really a good idea to use things that are dangerous, so that's not really a good reason there. And same here, it might be exciting, but it's not really a good reason why we use it. It would be a good reason not to use it. All right, here, match each reaction. So this one I really am forcing you to use mechanism to figure these out, and you need to know the difference between whether this. So first of all, you gotta recognize that the epoxide is to be attacked. It is the electrophile. This is creating a dipole, and so these carbons here are electron deficient and available for attack. So these are a variety of different nucleophiles you could use, and you just need to know, does it attack the more substituted side or the less substituted side? And that depends on if you're in basic conditions or acidic conditions. If you're in basic conditions, you operate by minimizing steric hindrance. Acidic conditions, you generally go by electronic factors and which side is more stabilized as a positive charge. So for that one, I'll just work through a couple of examples and then it's up to you to review this in the notes. This is a strong base, OCH3 minus. Basic conditions, I attack this way. So I'm going to have my 2 groups like that. My oxygen swings over, right? So that's this part right here. And then I had this carbon here is right here. And my OCH3 group added on. And I have methanol here so that I can neutralize that. So it's good to draw it out, and then you will figure out which of these options it is. So it really forces you to do that. All right, this is also basic conditions. This is acidic conditions. That's going to be a little bit different. Let me show you that one. So for acidic conditions, what happens is the oxygen gets protonated first, and this really emphasizes the positive charges in this molecule, so it really puts more positive onto here. And now I'm going based on stability of positive charge. So the bromide will prefer to attack there now. And that's mainly when it's saturated with carbon. So when the more carbons there are, the better. So this happens with tertiary. With secondary, it turns out it still attacks the less substituted with secondary. So steric hindrance may be an important factor then. Or that the electronic factors are not enough to overcome steric hindrance. So it's a good rule of thumb, though, in general, basic conditions is more anti-Markovnikov addition at the less substituted carbon. Acidic conditions, you go based on more stabilized positive charge. So Markovnikov addition, more substituted. So you need to go through this list and determine, is it more basic or negatively charged solution, or is it more acidic or positively charged solution, to tell the difference. The next question has to do with epoxide ring opening again, but same idea, different mechanisms, right? So this is acidic conditions. So which side are we going to attack? And do we attack from the top or do we attack from the bottom? Keep in mind this is a bridged intermediate. So I want to minimize steric hindrance. I want to attack from the bottom. But do I attack over here or do I attack over here? So that's up to you to decide. I just told you acidic conditions like Markovnikov or more substituted carbons. These like less substituted because of steric hindrance. Acid catalyzed ring opening usually starts off with the protonation of this oxygen, and that is very key in understanding all of these intermediates. Remember alkenes with Br2, oxymercuration. See, all of these reactions go Markovnikov because of this notion of attacking the more substituted side results in a lower energy intermediate. Because you're stabilized by induction, having more carbon groups around donates more charge in to stabilize that positive charge. So I want you to sort of think of these all as sort of being the same. So that has to do with the mechanism here. So I'll just give you a clue there. Epoxide oxygen gets protonated in the first step for acid, but in the first step of base that doesn't happen. Because you have a base, this acts as your electrophile, and you go ahead and you just attack the epoxide first in a basic condition. So that's the first step of basic. So that means nucleophile attacks at the less substituted carbon. Okay? So go through the rest of that on your own, see if you can figure that out. The epoxide is generally open from nucleophilic attack at the blank carbon. Well, we said in acidic conditions, more substituted carbon. And this is due to attack at a more stable partial positive charge. That will lead to a more stable intermediate, and the activation energy will be lower. Nucleophile always attacks on the opposite side of the ring. So in this problem here, we talked about the nucleophile is always from the opposite side of the epoxide. So if the epoxide is on the top, nucleophile will attack on the bottom. So it's opposite side attack. And so that's going to lead to trans molecules that are trans. See, here's this epoxide opening, and this is a trans diol. So they're always going to sort of be like that. Here, this is a multi-step involving this epoxide as an intermediate or as a reagent to use. So that's where I'm going to get all these carbons from. 1, 2, 3 carbons, 1, 2, 3. So how do I use this and this together? Well, remember, this is your electrophile because of the oxygen dipole. That's going to mean, something like that, right? So those are going to be my my electrophilic sites. And then what I want to do is have this be nucleophilic somehow. So maybe MgBr, and then that will attack right there. Okay, less substituted side because this is basic. Grignards are strong, nucleophiles strong bases. So it's going to attack on this side, which is great because then that gives me 3 carbon linear chain, 1, 2, 3. And this is going to be on the middle carbon of those three. Another technique that's really nice to use is numbering your carbons, right? So I know some of you have been doing that. So just recognizing where things go. And so my first step would be Mg to make this into a Grignard reagent. Step 2, use this guy right here. And step 3, after I do that, I'm going to end up with this. So obviously I need to neutralize that. So I'm going to use water or H3O plus dilute. And then I need to oxidize it. So I'll leave that part up to you. Any of those oxidizing agents is fine because this is secondary. So it can only turn into a ketone. So any oxidizing agent is fine. And this one here, again, it's a synthesis that involves putting a halogen on. So that's Br2, and heat or light is a radical reaction. And then I need to have the reactivity between those two carbons so that I have all these groups that I need to add on. So probably need to go to an alkene like that. And then I probably need to see, are these on the same side or opposite side? They're on opposite sides. See, this is trans, right? So dash and a wedge. So that means I'm probably going to make an epoxide in order to get that trans stereochemistry. And then one side will open up as OH, the other side is OCH3. Well, we saw that up here. If you want an ether, you can use an alkoxide instead of a hydroxide. If I want a diol, I'll just use hydroxide, and this will be an OH eventually, so I have two OHs. But here I want to make one into an ether and the other as a hydroxide. So I want the OCH3 to add on to here, but then do I need acidic or basic solution to make it add at the more substituted site? Well, I think I need to make that acidic then. So HCH3OH, but I need a little bit of acid just to catalyze this protonate here and then have the methanol attack. Because remember, methanol is a weak base, so it really needs enticement to attack here. So that's why I'm protonating here. That really makes this more reactive. So that's how the catalyst works. Okay, so do you guys got all that? Okay, so step 1, Br2, then we need a strong base to eliminate here. I'll leave that part up to you. Remember, I don't want this one, right? I don't want this alkene, I want this one, Zaitsev. Then I want to epoxidize that, so you figure that out. And then I need methanol in acidic solution to get attack here instead of the reverse. If I use NaOCH3, that's basic solution, I'm going to get attack on the other side here, OCH3, and then I'm going to end up with the opposite result. And this is going to be this or wedged plus an enantiomer. So yeah, just be really careful here that you really have control over which group goes where, and is it syn or anti, cis or trans, okay? And the last problem is a little more complicated. I know you guys are taking biology, and so I'm trying to find more examples of ways to incorporate that. Also interesting molecules and drug synthesis and things that are interesting. This is from the book. This is a synthesis that involves using an epoxide and changing it into this functional group. So it's a cyano group off the alpha carbon, and this is a ketone. So some ideas for this without giving it away. We're going to need to have something attacking here, right? That's a group. And maybe, because if I don't want anything attacked here, otherwise this will open up and I'll end up with a carbonyl on the end carbon here, right? I don't want that. So really I have to have a nucleophile attack here. You figure out what nucleophile will result in that. And then what happens to this part, it's not going to turn into a ketone yet. So you're going to have another step to take care of that oxidation. All right. Okay, good luck everybody.